Everyone, and welcome to today's webinar, Real-Time In-Situ Insights, Dynamic Mapping with 4D STEM. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We'll attempt to answer any questions for the speaker at the end of the presentation. If we don't get to your question, we'll follow up via email after the webinar. Now I'd like to introduce the speaker for today's webinar. Ben Miller has been working on the development of in-situ techniques since 2010, when he began his master's degree project to illuminate TEM samples with visible light. His PhD, working in the group with Peter Crozier at Arizona State University, focused on the development of operando ETEM to simultaneously observe catalyst nanostructure and measure catalytic activity inside the TEM. In 2016, he joined Gatan as an in-situ application specialist. In his role, Ben collects imaging, spectroscopic, and 4D STEM data demonstrating the capabilities of Gatan's in-situ products and presents the results around the world. He also provides applications training and support to researchers and helps to specify the capabilities of future in-situ TEM equipment and software. Now over to Ben.
Yeah, thanks, Jonathan. I'm excited to present today about how we can get real-time in-situ insights with 4D STEM, doing dynamic mapping in real time with 4D STEM. So the first thing that I'll show today is the operating principle of 4D STEM. And this is a really nice video put together several years ago by Colin Ophis, and just showing what do we mean when we say 4D STEM. Hopefully most of you are familiar with this already, but as we scan a sample, in traditional STEM imaging, you would just get one intensity value from the annular detector, your high angle annular detector, for example. And so with this single intensity, as you scan across the sample, you build up an image. But in 4D STEM, we can additionally have a camera below the STEM detector that enables us to capture an entire diffraction pattern at each scan position. And so you get 2 dimensions as the probe scans across the sample, and so 2 dimensions in real space, and then 2 dimensions in reciprocal space or diffraction space from the camera at each probe position. So this is why we call it 4D STEM. 4D STEM is really an entire family of techniques because there are many different ways that you can set up your diffraction pattern, set up your probe, and a lot of different ways that you can process and analyze the data afterward. But this entire family of techniques is often called 4D STEM. So there are actually 3 different features that are new in the latest version of DigitalMicrograph that we just released earlier this year that are all related to 4D STEM. And I'm not going to talk about all of these today. I'm really going to be focused on this third one, what we call survey mapping. But I just wanted to mention very briefly these other 2. We have what we call STEMX OIM for orientation mapping in DigitalMicrograph. And there's actually an entire webinar about this on our YouTube channel. So we post all of these webinars that Gatan presents on our YouTube channel. So you can go there and see the webinar for STEMX OIM that was just released a couple weeks ago. And then later this week, you should be able to watch this webinar that I'm giving today on survey mapping. We also have a new feature oops, sorry. We have a new feature for custom scan as well, where we can flexibly determine how the sample will be scanned. And I'm not going to go into any details about that today. I'm not going to show that today. But there's a lot of exciting things that could potentially be done with custom scanning using the DigiScan 3. Okay, so this data set that I'm showing here is not using this new survey mapping technique. This is the sort of in situ 40 stem acquisition that Gatan has enabled for several years now, where we can capture an entire series of 4D data cubes over time, and then very easily process these to produce videos. And in this particular experiment, we see this was done in liquid. So this was using an in-situ chips holder that has these very thin nanochannels, which is great for doing 4D STEM. And so we can watch in the STEM image, we can see the morphology of these particles. We might be able to determine the growth rate of these. But it's more difficult to determine where are the grain boundaries. These are polycrystalline, not single crystals. And so it might be difficult to determine just from the STEM data, certainly at this resolution and with this very large field of view, to determine where are the boundaries of these crystalline regions. But because we are also collecting 4D STEM data cubes, an entire series of 4D STEM data cubes over time, we can go back and process this data and find where are the different nanocrystalline regions in this material that's being formed in situ in the microscope. And so this particular analysis here is what I call a maximum spot map. So it's not proper orientation mapping. But I'll show on the next slide here, what do I mean by a maximum spot map? What is this processing that I'm doing? Because we'll see a lot of this in this presentation today. So the maximum spot mapping technique is something that I made up a couple years ago. I had never seen this done, but I thought this would be a good way to very quickly and easily process 4D STEM data, and specifically an entire series, an entire in situ series of 4D STEM data. So what I do here is for each pixel in the 4D STEM data cube, we have a diffraction pattern. And so I want to find what is the brightest spot in this diffraction pattern. So in this case, this is trivial, right? There's really only one spot outside the center here. But I want to find the angle of this maximum spot relative to the center. And to do this, I'm going to exclude some center region, right? I don't want the algorithm to find the center spot. I want it to find the maximum spot outside the center. So excluding some center region, I find the angle, and the angle then corresponds to some hue of this color. And the intensity of this brightest spot corresponds to the brightness of the color in this final map. And if I bin the data first, this makes it more computationally efficient, and we can very rapidly find what is the brightest spot in this diffraction pattern, and do this over the entire 4D STEM data cube, and then extend this to apply the same processing to every 4D cube in an entire in situ 40 stem data set. One of the benefits of this particular technique is that you are only using the highest signal information. So if most of my diffraction pattern is quite noisy, my intensity is low because I'm scanning very fast, for example, I'm just using the information from the brightest pixel, the pixel with the highest signal, and I'm ignoring all of the other noise in the image. And so this actually gives me a very high signal final map. So for using 4D STEM for in situ experiments, there are some challenges, certainly, and I'm excited about how this new approach that we called survey mapping can mitigate some of these challenges, perhaps not eliminate them, but mitigate these challenges for using 4D STEM for in situ. The first challenge is really the large volume of data. So this data set that I was just showing is only about 30 gigabytes. To me, as someone who has done in situ TEM for a long time, 30 gigabytes does not seem very large, actually. That's quite manageable. But it's very easy to produce in situ 4D STEM data sets that are hundreds of gigabytes. And so these large volumes of data can become a challenge. Of course, these large volumes of data are also an opportunity, right? So the beauty of 4D STEM, one of the great benefits of 4D STEM is that we have a huge amount of information in these data sets that you can go back and process the data in a variety of different ways, get different types of information from different types of processing. And that is one of the values of 4D STEM. But this opportunity that comes with a large amount of data can also become a challenge as you get into hundreds of gigabytes or even terabytes of data. Another challenge is that four-dimensional data is inherently non-viewable, right? I cannot look at a four-dimensional object on my two-dimensional monitor. I have to process and visualize the data somehow in order to display a four-dimensional data set on a two-dimensional screen. And adding the time dimension now for in situ so that we have now five-dimensional data, this is even worse, right? We have even more dimensions that somehow need to be displayed to the user to understand and to visualize what's happening with my sample. And all of this means that it can be difficult to rapidly determine either the data quality, do I have artifacts in my data? Am I seeing the information about my sample that I want to see? And to interpret results, you know, is the science that I was expecting, is the transformation that I expected at a certain temperature actually happening? It can be difficult to determine this in real time. And so this brings me to maybe the main challenge here for in situ specifically. How can I make good decisions about what to do next in my in situ experiment? If this is a new sample, a new experiment, I'm trying new experimental conditions, how do I know that I've reached the temperature that I need, or the gas composition is causing the transformation that I expected? If I'm looking for something in the four-dimensional data or the five-dimensional data, will I be able to see that in real time? And if not, Does that mean I collect my data and then I have to go back next week and process it and visualize it, and then find out that my dynamics that I was expecting didn't happen. My transformation didn't occur. And so I'm going to have to go back and change my experimental parameters. It's much easier if I can visualize and analyze my data in real time while I'm still sitting at the microscope. And then I can very quickly make changes to the in situ the in situ environment, or to the microscope, right? To change the microscope parameters to get better quality data. But I can only do this if I can understand what's happening in real time. This data set here at the bottom left, I'm not going to spend a lot of time talking about this one, but this is proper orientation mapping, unlike the data I showed before. Down in the bottom left, this is actually doing orientation mapping using Pi40 STEM in DigitalMicrograph. And so if you are interested in that, in using Pi40 STEM in DigitalMicrograph, there's actually a poster on our website on the 40 STEM page. But this is the last that I'm going to talk about Pi40 STEM in this webinar. So what is the ideal solution to these in situ 40 STEM challenges? I've talked about what is difficult, but how do we solve this? What would be the ideal approach to overcoming these? I think first of all, we would want to be able to process all the 4D data in real time with results being displayed live during acquisition. And I would want to not just have one or two algorithms that I can use, but be able to use whatever algorithms I want for my particular experiment, right? So in different experiments that I do with 4D STEM, I might want to process the data in different ways. So I might want to use different algorithms each time. I might want to use someone else's code, right? That I saw them present at a conference and they sent me a link to GitHub, and I want to use their code to process my data in real time. And of course, I would ideally want to do this without slowing down the acquisition. I would want this to result in a massively reduced data size so that I don't necessarily have to take with me all of the data, all of the tens or hundreds of gigabytes of data. And ideally, I would also want all the 4D data cubes to be stored in real time to some remotely accessible storage facility where later, if I want, I can go back and look at the full 5-dimensional data set in more detail, right? But maybe it turns out that the processed data is all that I need. But maybe for some experiments, for some bits of data, I might want to go back and look at the full 5-dimensional data set. I would also want to be able to save, of course, these live process results and play them back. With the full 5-dimensional data synchronized as well, and also any in situ conditions, right? So if I'm doing an in situ experiment, it's not enough for me to see the in situ 4D STEM data if I don't know what were the in situ conditions at each moment in my experiment. So the current solution from Gatan for these challenges is we call survey mapping. And I've highlighted in blue here the things that it can already do. So we can already process all the 4D STEM data in real time and display those results live during acquisition. We can use different algorithms, and I'll talk more about that, how we can do that with scripting, as well as some built-in algorithms in DigitalMicrograph. I've highlighted the next 2 points in a slightly different blue color because these, I would say, are partially fulfilled in DigitalMicrograph today. So we can use other people's code because we can use scripting. But as I'll explain, the current survey mapping tool is only using DM scripts. And so this makes it more difficult to just take someone's code from GitHub and immediately apply it. But we can apply other people's code, and I'll talk more about that at the end of the presentation. Without slowing down acquisition would be very nice, and sometimes this is possible, right? So in the data set that I'll show today, I believe we didn't slow down the acquisition just because of the processing, but this really depends on the type of processing you're doing, as well as the speed of the camera that you're using, how fast is the data coming in, what is the PC that you're using to do the processing. There's a large number of factors that influence whether you can process all the data without slowing down the acquisition. So I'll color that in a different blue color, but sometimes this can be true. Of course, we always are massively reducing the data size, and I'll talk about that more later. We don't currently save all the 4-dimensional data cubes in real time, so we have to choose, right? You can either use the in-situ 4D STEM tools in DigitalMicrograph to store an entire series of 4D data cubes, or you can use the survey mapping approach to just save the 2-dimensional processed results and not save the 4-dimensional or 5-dimensional data. We do enable you to save these live process results, as I'll show in the next few slides, and we can easily play these back and synchronize these with the in-situ conditions over time, as you'll see. So up to this point, I've been talking a lot about in-situ, and I'm the in-situ application specialist at Gatan, so that makes sense. But there is another way that we can use this survey mapping tool that has nothing to do with in-situ, and that is to use the tool as sort of a live view for finding the right part of the sample. And so that's what's being shown here. We're doing a live DPC processing of the 4D STEM data just to find the right part of the sample and to confirm that we see what we expect to see in the DPC result. And then we could easily capture a much higher resolution acquisition, but this survey mapping tool gives us sort of a live view for 4D STEM or a live view for EELS spectrum imaging. So this tool, this is what the tool actually looks like in DigitalMicrograph, this survey mapping tool. And here you can see some of the setup for a particular type of processing for virtual apertures. This is a new tool in DigitalMicrograph version 3.6.2. This is a free upgrade as all of the DigitalMicrograph versions. If you have 3 point something, you can always upgrade the software for free. And so this is no different. If you already have the capability to do in-situ 4D STEM in DigitalMicrograph, then when you upgrade to 362, you'll get this survey mapping tool with all the capabilities that I'm showing here today. You can use this tool to process 4D STEM data, which is the focus of this webinar, but you can also use this same tool to process EELS data or EDS data live. And again, there are two main ways that I see people using this tool. One is to just find a good region of the sample using this as sort of a live view for spectrum imaging. Or another approach that I'm focusing more on today is to record a long in-situ experiment with live visualization and less data that you need to store. So the processing techniques that are available currently for 4D STEM and the survey mapping tool are virtual apertures, DPC, and then DM scripted processing that I'll demonstrate in a few minutes. Processing available for EELS includes elemental maps, least squares fitting, you can do thickness maps, and of course also DM scripted processing. So one of the key benefits that I mentioned earlier is data reduction, right? The ability to reduce the data size. In-situ 4D STEM data sets are inherently large. And so the two that I've showed already today were 18 gigabytes and 29 gigabytes. A data set that I'm about to show would be 240 gigabytes of in-situ 4D STEM data. And those are these big cubes here. I don't know if you can even see these or if you notice them. There are very small cubes next to these that represent the size of the data set after processing. So the volume of data is really significantly reduced, orders of magnitude less data, going from tens or hundreds of gigabytes to just a few megabytes of data to store the entire in-situ video here. And so these are the process results, again, from these three different in-situ 4D STEM acquisitions. Now I want to show what does this really look like in the software? What would you see if you were acquiring a data set like this, acquiring an in-situ data set with the live processing applied? And let's just go straight to the most complex setup, which would be a scripted processing, right? I want to do my own processing. I'm going to do this maximum spot mapping that I showed before. And so I can do this with scripts. So first, I just install my script. This is a DM script file. And so that's all there is to it. Just install that as a library. Now I'm going to do some initialization of the processing. So the script that I have enables me to, after I start the live view of the camera and I start the live view of the scan, now I'm going to click a button to initialize the script. This will give me this circle in the middle that allows me to choose what region to exclude as I try to find the maximum spot in the rest of the diffraction pattern. So now my script is set up. It's tested this, right? So that I can be confident it's going to run when I start the live view. And so now I'll click this live view button and we can see the process data start to come in the bottom left here. Up above is just the standard STEM dark field image. And then if I click record, this will start again, but now I'm actually saving the data in real time. So let's go to the next bit of this video. Here, I'm going to start a temperature recipe. So I'm actually controlling a DEN Solutions wildfire holder within DigitalMicrograph here, and starting this temperature recipe where I oscillate the temperature above and below the melting point of these tin nanoparticles. And so when I go above the melting point, most of these particles disappear because they become amorphous. And when I go below the melting point, then we see them reappear in all different colors because they recrystallize in different orientations. But the point that I really want to make here is, can I make good decisions about what to do next in my in situ experiment? And I would say that yes, because I can see what's happening in my process 40 stem data, I can see whether, maybe I'll play this again, whether the particles really are appearing and disappearing as the temperature goes above and below the melting point. I can see if the conditions that I'm using are the right conditions for this in situ experiment. Now, this experiment I've done many, many times, so I really don't need to make any decisions about what to do. But if this is a new experiment that I'm doing, a new in situ conditions that I'm applying or a new sample, it's going to be very important for me to be able to see what's happening so that I can make good decisions about what to do next. Of course, after I press record again to stop the acquisition, then it's going to finish that last pass, that last scan, and then automatically open up this data set. And I can very quickly play this back and immediately see what happened in my in situ experiment. And I can see the temperature plot as well. And I'll go to the last bit of my video where I just, I'm going to change some of the display parameters for my plot and just make this look a bit nicer. And I can see exactly where I am in the temperature plot as I play back the data. I can also click within this temperature plot to go to exactly that position in my in situ data set. And this entire workflow, this was all one video that I recorded. This whole workflow was recorded in just 11 minutes. So it was very quick and easy to collect this data. And the resulting video is only 1.9 megabytes of data. Rather than the over 200 gigabytes that would have been collected if I had collected an in situ 40 stem data set. So the processing that I just showed was using a script, and maybe some of you are thinking, wow, how can I do that? How can I write a script like that? This is a very simple example, a minimal example of processing data. This is not the script that I just showed applied to my data, but it's a very simple example that really does give a result in DigitalMicrograph and would work with this survey mapping tool. As I said before, this is a DM script, and it must be a DM script. Python processing is not yet directly available for survey mapping, but we can use a short DM script to call Python code and still use Python processing if it's wrapped in this short DM script. So here's an example. This is doing the same thing as the very simple script that I had just showed, but using Python. So the bits in red here, these lines from 16 to 19, are the Python script that I'm using to process the data in the same way as this very simple DM script. So I could do this. I could also, instead of writing the Python code directly in my DM script, I could call a .py file and process my data with Python as long as it's wrapped in this short DM script. So to summarize here, while 40STEM is powerful, in-situ 40STEM can produce vast amounts of data. And so this really makes live processing even more attractive. DigitalMicrograph now has this survey mapping technique that we can use to produce real-time results with real data reduction in DigitalMicrograph. And we can even use scripts to perform custom data processing in real time, as I just showed. So with that, I will stop and let you submit questions. I'm happy to take questions and try to answer them as best I can. As Jonathan said at the beginning, if we don't get to all the questions that come in right now, we will email you individually to answer your question.
Thank you, Ben. There are a few questions. I'm going to try and ask a couple of them as time allows. First one, which camera is used for in situ liquid 40STEM?
Yeah, so for these experiments, I think I used several different cameras to collect the data that I showed in this presentation. I used the Metro, which is a direct detection counting camera. I also used Stella, which is a hybrid pixel detector based on Dectris's ELA or ELA camera. And so we call this Stella. We can install this at the end of GIF. And also, I think one of these data sets was acquired using the K3. Again, a direct detection counting camera, maps detector that can go above or below the GIF.
Okay, the next question is, what other in situ holders can you support in DigitalMicrograph?
Yeah, so, okay, let me get back to that because I just thought of something I meant to say about the cameras. You can use other cameras, right? So any of the cameras that Gatan sells today can be used for 40STEM. And so it's possible to use any of our cameras, Clearview, Rio, Metro, K3, Stella, hopefully I'm not forgetting any, the GIF camera. Any of our cameras can be used for this with STEMX. STEMX is the box that synchronizes the scan with our cameras. Okay. So for this question about in situ holders, so we can control the Den Solutions heating holder. As I showed in this presentation, we can control the temperature actually of any, the Den Solutions wildfire or their climate gas cell holder or their lightning heating and biasing holder. Any of those, we can control the temperature directly within DigitalMicrograph. We can, of course, control Gatan heating and cooling holders if they're using the latest temperature controller. So we call this the 1905 temperature controller. This is the one that has a touch screen. So if you have a temperature controller with a touch screen, you can connect that to DigitalMicrograph and control our heating and cooling holders directly from the software. But you can also not control other holders, but you can integrate data from Protochips holders that use their Axon software, as well as from DEN Solutions holders that use their Impulse software. So if you are using DEN Solutions Impulse to control the biasing of their Lightning holder, for example, you could get the bias information in DigitalMicrograph, have it all integrated like I showed today. You just can't control the biasing from DigitalMicrograph.
Okay, and in order to integrate these holder data, do we need to purchase any licenses? How do we do that?
Yeah, so the good news about this is that the licenses for this are free. You may already have the license already, and it just DigitalMicrograph needs a setting to be set so that you can control your holder. But if you don't have the license that's required, you can request that from your local Gatan salesperson or distributor, and those are free licenses.
Another question about the experiments is they're asking if do you have a solution to address drift during in situ 4D STEM acquisition?
Yes, great question. So we do for spectrum imaging in DigitalMicrograph for eels. For many years, we've had some drift correction in spectrum imaging. And so when we added 4D STEM as a technique in DigitalMicrograph, of course, it could do this same drift correction during acquisition. But recently, we've actually improved the drift correction. Starting in GMS 3.6.0, I believe, we really expanded the capabilities for the live drift correction so that it measures the drift from the data itself. And this is really great because it's faster than the approach we were using before, where you had to scan some other region to measure the drift from that other region. Now we can directly measure the drift from the data and do this very quickly. And so the drift correction is actually quite nice for these in situ 4D STEM acquisitions. And you can also do drift correction in post-processing as well. So the exact same tool that we would use to drift correct an in situ TEM video collected with one of our cameras, that same tool can be used directly on one of these in situ 4D STEM data sets, and it will measure the drift from the 5-dimensional data. Or you could measure the drift from the HOTF image, the STEM image, and apply that to the 5-dimensional data. So it's quite flexible. You can do both the live drift correction in real time and a post-acquisition drift correction.
Okay, maybe the last question I will ask, it's about scripting. How can I get more details about how to write my own script to do live processing of 4D STEM data?
Yes, good question. So probably the best thing to do is to email me directly. My email is here at the bottom left of the screen. So you can send me an email and I will send you the same fabulous instructions that our software team sent to me on how to do these scripts. I guess one other thing that I'll say is that Copilot, or probably any AI tool, can be very helpful with this as well. And that's something that I'm really excited about, the potential for using Copilot and other AI tools to make it easier to write DM scripts, for example, or to take two scripts and merge them together to do the processing from someone's Python code, but apply it to this survey mapping. But send me an email and I can get you more details.
Okay, I think if we didn't get to answer your question now, we will definitely get in touch with you via email and try and answer all of the questions submitted. And I think that's for today, Ben.
Yeah, thanks, Anna.
Thanks everyone for joining us and have a great day. Thank you.